and to ask some questions. First, do you think that you can hold the whole biology lab in your hand? Other question, do you think that you can create hollow microneedles just with light? Can you add electronics in your products without using any PCB, printed circuit board? Can you make complex mechanical parts with a single wire? And more exotic, can you sculpt a Nazca hummingbird with just a single rod? So I hope that at the end of this talk, I will convince you that it's possible to say yes to those questions thanks to micromanufacturing. So before we start, why micromanufacturing? Actually, the goal is to miniaturize the products in product development. The goal of miniaturizing is to maximizing the outputs while minimizing the inputs. And you can get a lot of advantages out of this approach. First, you can improve reliability and robustness of your products. Gravity will act on very small parts, weight, very light parts, and which improves this robustness. Thanks to miniaturization and micromanufacturing, you can integrate more functions in a smaller volume, which is very interesting for smart products, for instance. This allows a high degree of customization. You can reduce production time and cost due to the very small amount of material you are playing with. And for the same reason, you can also reduce the environmental footprint because you play with small volumes of materials, you generate less waste, and you also need less resources to store, to transport, and also to recycle those parts. So, before going any further, I just would like to highlight what micromanufacturing is not for the talk of today. You have heard probably about microfabrication, which is more oriented towards all those processes, silicon-based processes, which are used in microelectronics, CMOS industry, like photolithography, etching, and so on. So that will not be part of the discussion today. Microproduction, also, that's something that you heard often. It's more the manufacturing of products in small quantities or by using small manufacturing facilities. Microengineering is also something that you heard about. It's more global, it's a more global approach where you consider conception, design, simulation, fabrication, of course, programming of complex and global systems. And of course, miniaturization is a very nice word, but it doesn't mean a lot of things because it's just making things smaller, but you don't have a real dimensional idea behind this wording. And finally, microproduct is also something which makes sense for our talk today, but it's a product with very small dimensions, very small volume of materials, and you will see that micromanufacturing is not only for small products. So, this is what it's not. Now, what is micromanufacturing? Of course, in micromanufacturing, you have the word manufacturing, so it's a transformation of raw materials into products that have been specifically designed for a certain application. And most important, you have micro, and that is what I would like you to keep in mind for the rest of the talk. It's where you have at least one functional detail in the submillimetric down to the micrometric range. So that means you can have a very small part, small volume, so all your details are in this dimensional range, but you can also have macro products with micro details where the function is achieved with details in this dimensional domain. So, micromanufacturing is not just a matter of reducing the size of the tool that you use. So you need to face a lot of manufacturing-related factors due to the dimensional range where you go. You need to consider material properties versus tool interaction and thermal effect and so on. Structural strength and stiffness of the material at this level of details, of course, is very important. handling, clamping, releasing of the parts that you manufacture at this dimensional level is also of importance. Residual stresses and weakened surface integrity, also a source of concern. Tool aspect ratios and accessibility for those tiny features is also very important. And of course, surface roughness, because you play at the level of the grain size where you have interfacial friction and dislocation which can occur, is also very important. And of course, at this level, of course, residual tool radius can create a specific effect, which is not the case when you are on higher dimensions. So it's important to have the right dedicated technologies and approaches when you go into this dimensional range. So welcome to the micromanufacturing lab that we have at Sirris. This is just part of it where we have most of our micro machining equipments. And we have internally, under the same rooftop, all those techniques available and all those families of techniques from subtractive, additive, replication, selective material deposition, and of course, everything related to assembly and metrology. And for the rest of the talk, I would like just to highlight some of those techniques which are typically classical techniques like the one that you can see here, which are pushed towards the micro domain. Let's start with subtractive family, with milling, micro milling. So it's very famous, of course. So on the video here, you see a typical example of a process where you start from a blank substrate and you remove material to shape it according to the 3D shape that you want to achieve. And what is interesting, of course, is the availability of tools down to 10 micrometers diameter. That means that the minimum feature size that you can obtain by milling is in this order of magnitude. And moreover, there are specific tools which are diamond tools. So it's a synthetic diamond which is mounted on a shaft, very precise, which allows you to achieve very low surface quality, very good surface quality. In polymer material, for instance, you can have optical surface by direct milling on PMMA, for instance, with those equipment, with those milling tools. Another family of subtractive technique, of course, is electro-discharge machining. So it's where you use an electrode that you bring almost into contact with a substrate, a conductive substrate that you want to machine. And when it's almost in contact, you're going to generate sparks. And those sparks are going to remove very locally the material out of the metal. So it's very convenient because you can play with a lot of electrodes to shape the metal with this technique. And one of the most simple electrode that you can use is just a wire, a single wire. That's wire EDM. And you can play with, there's a video here, and you can see here what is going on along the wire. That's where the sparks are generated. And you can achieve very fine cut with this wire, which can be as low as 20-25 micrometers diameter. And you can achieve very nice parts with this wire cutting technique. And even complex parts can be achieved with this technique by playing just by the position of the part with respect to this wire. Furthermore, still in the EDM family, micro 3D EDM milling, that's also another technique based on EDM process. But here you play with a rod, which is your electrode. And again, it's a technique based on EDM, and there is no contact between the electrode and the part which is machined. And here you can shape the electrode according to any kind of shape that you want. It can even be a very tiny electrode of a few micrometers diameter times a few millimeters diameter for deep drilling application, for instance. And you can really make very fine details with this electrode. Again, it's an EDM technique, so there is no direct contact of the tool with the substrate, so no stress, no thermal stress, no mechanical stress, very precise technique. So this is the kind of feature that you can achieve. That's a mold insert for microfluidics, for instance. You can really play at the level of the micrometer, and with very good surface quality, you can achieve optical finish 15 nanometers array in steel by direct operation with this technique. You can also derive the very fine spark generator to make micro die sinking EDM with very tiny electrodes, as you can see here, to transfer the shape into the metal very precisely. So that was for the subtractive techniques. Now let's go into the world of the additive technologies. And this is an example of a multi-scale micro 3D printing technique that we have in-house. It's a combination actually of two modes. First mode is the DLP micro stereolithography technique, where you can see here the principle. Actually, you are going to project pictures and contrasted images in order to build layer by layer your object from a resin which is liquid at the beginning and that you can cure thanks to the light. Where there is light, the resin is going to cure. Where there is no light, the resin remains liquid, and then you can build your object this way. And what is interesting here is that you can also have a second module which is mounted on exactly the same workbench, which is a laser, and it's a process called multiphoton polymerization, and you can achieve 1 micrometer resolution with this process. So by combining all those techniques on the same workbench, you can achieve this kind of multi-scale micro 3D printing job. This is a part that I can keep in the hand, and it's written Micromanufacturing there. And this is a view of what has been printed by DLP. And on the dot on the eye, this is the kind of features that you can achieve, microfluidic features, 1 micrometer resolution on the same workbench. So it's a very large scale that you can scan with this technique in 3D printing. That's an example of, that's a video of an example of, that video. Thank you. That's a microfluid, oh, no, the previous one, please. That's here. That's an example of a microfluidic chip which has been printed by this technique in a few minutes. So you can see that it's completely functional. You see the liquids here, which is pumped into the channel, which are printed by this technique. So very efficient technique to create this. Okay, that we have seen some subtractive technique, additive technique. Now let's go one step further in everything related to selective material deposition. It's printing, actually, but not 3D printing. It's printing for the functionalization of the surface. And we have different techniques available in this family, depending on the resolution that you want to achieve, the throughput that you aim at having with this technique. But the principle is always the same. You start from a material which is liquid or like a paste at the beginning, and you are going to deposit this material selectively on the surface. And here is a first example of a screen printing technique. This is how it works. So it's widely used in the graphic industry, for instance. You have a mesh here, which where a pattern has been engraved in a photo emulsion, and the idea is to use a paste that you can apply on this mesh, and the paste is going to be transferred through this mesh according to the pattern of the mesh. So you can really easily transfer the paste from the mesh to the substrate, which is underneath. And that's very nice to obtain this kind of feature. That's electronics, printed electronics. You see circuits which have been printed, some protective layers of dielectrics, which have been printed directly on the substrate, which is not a PCB anymore. Your substrate, your product, is your PCB, thanks to those techniques. So it's a very convenient way to introduce electronics in your products by just printing the circuits on it. Another example on the other side of the range in terms of dimensions, it's aerosol jet printing. Same principle, you start from an ink, you create an aerosol, and those droplets of the aerosol, you are going to send them in a nozzle to focus this beam to the substrate that's on which you want to print. So you can print antennas, conventional circuitry, but you can play on 3D surfaces with resolution of 20 micrometers for the smallest ones. An example of LED which are integrated in microfluidic chip, fed with those circuits, printed directly on the chip before we can close the chip. So, subtractive, additive, replication, printing, now replication techniques. So the principle is always the same, to start from a mold with a shape, a specific shape, and to inject material, thermoplastic material, to take the shape of this mold to create replicas of the shape of the mold. So typically, this is an example of injection molding. You start from pellets of polymer that you send in a screw where it's heated and sheared in order to lower the viscosity and to bring the material into the mold, which is closed when the injection is done. Now, injection is performed, cooling down of the material. When the material is hardened, you can eject it out of the mold, and the cycle can start again. So very convenient and very common way to replicate polymer parts. And different techniques, again, are available for the micro domain to create small parts. Those are micro-optical lenses directly mounted on their frame, injected with the micro-injection molding machine. But again, if you remember at the beginning, micromanufacturing is not only small parts, it can also be big parts with micro details. And this is an example of a part, macro part, with micro details, small channels which are not bigger than a human hair, which are engraved in the part. Of course, to do that, you need to make molds, so you need to rely on the techniques that I have explained earlier to make those molds before you can create those replicas in polymer with very fine details that you can obtain with those techniques. So, there are many other supporting techniques that I will not go into detail on that, but of course laser, micro-texturing to apply specific textures on your substrates, soft UV embossing to make other duplicas, thermoforming, nickel electroforming are also very interesting techniques that you can rely on for this dimensional range. Okay, so yes, and last but not least, of course, very important at this level of details, you need to be equipped with the nice equipment to map and to characterize all the surfaces. And there is no ideal equipment. You need to rely on a batch of equipments to be able to achieve all those characterization jobs. Okay, so that's just a summary of what you can rely on for micromanufacturing to play at this level of details: subtractive, additive, printing, replication, assembly, and metrology, as we have seen. And for the rest of the talk today, I would just like to show you some examples of applications and parts which are made with those techniques for different sectors. All the sectors are concerned by this dimensional range, as you will see. Let's start with medtech and healthcare. That's a very important sector where a lot of developments are made now with those techniques to miniaturize the devices in this domain. So you can have flow cells with different sensors, biosensors integrated, different wearable kits for therapies and so on. Microneedles for fluid dispensing, very nice part of equipment if you want to consider painless drug delivery. a very big topic, microfluidics lab on a chip, where you can integrate a lot of functions on one single piece of plastic. You can make mixing, reaction, incubation, PCR, filtration, detection on just one single plastic part made by those different techniques. The same for chemistry and pharmaceutical industry, those bioreactors and microfluidics reactors for continuous flow chemistry applications. Portable devices for sample preparation and quality control in food industry, very important to be able to perform those kind of analysis in the field directly with no need to go back in a central lab as it is the case for the moment. Environmental application with printed sensors, with integrated sensors, and this is an example of a gas sensor which is integrated on a 3D printed part where SMD components are integrated and the circuitry is just printed on top of the surface. No PCB anymore. For space and aerospace and aeronautics, lightweight components, lightweight integration based on printed electronics, and also test support equipment required also a lot of efforts in terms of miniaturization. In automotive, of course, lighting is very important with micro-optics, but also a new trend in this domain, which is in-mold structural electronics, which actually combines printed electronics and injection molding in order to integrate directly in the plastic part the electronic components and the electronic circuitry in a monolithic part. So I hope that I've been able to convince you the interest on considering micromanufacturing, which is those techniques and strategies for the manufacture of products and or features that have at least one functional detail in the micro range up to the sub-millimetric range, which provides a lot of advantages from very small size, optical, mechanical or fluidic parts which can be machined, functional micro features in micro products. It's a minimally invasive addition of functions in products or processes which can be achieved with those techniques. You can increase reliability, robustness, reduce production time and cost, reduce environmental footprint with those techniques. And so, just to finish, if I come back to my challenges at the beginning, can I hold a biology lab in my hand? Yes, you can. By using micro 3D printing, micro milling, micro replication, micro assembly, you can do this. Can I create hollow micro needles with light? Yes, you can. Micro 3D printing, micro injection molding allows you to do that. Can I add electronics in my products without PCB? Yes, you can. Micro printing, printed electronics in mold structural electronics helps you to do that. Can I make complex mechanical parts with a single wire? Yes, you can, thanks to micro wire EDM. And finally, can I sculpt Nazca hummingbirds with just a rod? Yes, you can, with micro 3D EDM milling. And let me introduce the smallest Nazca hummingbird in the world achieved by this technique. Thanks a lot for your attention, and I will be happy to answer your question if you have any.
Thank you, Denis. I've been dazzled and slapped around the head with technologies and methods for all kinds of micro manufacturing. But one last question is quite intriguing me. You are talking about your expertise and your research in the micro manufacturing lab.
Yes.
Now, suppose that those people here have any idea or any project they want to implement or know more about. I just would like to know, Denis, where is the lab? Can they have a demo tour?
Sure.
And how do they make an appointment?
Just by contacting me, there is here the website when you can find all the data and some more information. There is also a virtual guiding tour of the lab. So just feel free to contact me. That's really our mission at Sirris, to bring support to companies in this kind of domain. So just feel free, keep this address in mind, and I will be happy to welcome you. And the lab, most of the equipments are located in Sirris, near Liège, Leuc.
Perfect. So if you have any questions or you would like to make an appointment, please join Denis at the bar for a coffee or a pint or something, and you can make a personal appointment with Denis. Thank you very much, Denis. And before you go home, of course,
Thank you very much.
It's not micromanufacturing, but it's perfect. Thank you very much. Bye-bye.
Thank you.